Okay, in this video we're going to run through some electrolysis exam questions. There are three, and I've deliberately chosen what would be considered the more challenging exam questions. So we're going to look at them, think about how we could approach those questions, and then also think about what they're looking for when it comes to the actual answers. So we start with this first question. So they tell us that in figure 1, they've given us the apparatus used to electrolyse silver nitrate. And they give us the formula of silver nitrate, but then they also tell us that it's a solution. So that's really very important. Now, the thing about electrolysis is we're splitting up ionic compounds, so using electricity. So it's very important whenever you're approaching any electrolysis questions, and this one is a particularly hard one, that you are confident and sure about the ions that are present. So we are given the substance silver nitrate. They give us the chemical formulae, and so we can think about what ions make silver nitrates, so silver ions and nitrate ions, and metal ions are always positive and non-metal ions are always negatively charged. So there's our silver nitrate, and this is where you've got to be very careful. If you see that word solution, you've got to underline it, you've got to highlight it, you've got to asterisk it, you've got to whatever, because you've got to remember that now we know that this is an ionic compound that's dissolved. That means that we also have two other ions present. So we also have hydrogen ions and hydroxide ions present. So we actually have 4 different ions in this solution, in this mixture, and that's going to be important when we come to look at the actual questions, where they're asking us to name the products discharged at each electrode. They've given us the setup, so this is also a useful picture for other questions when we think about the setup for electrolysis. They've told us that filament bulb lights up, so the filament the bulb isn't vital or isn't necessary for electrolysis in the sense of making it work or not. But what it does do is the fact that it says it's lit up means that the electrolysis is taking place. So we are getting products discharged at each electrode. They've labelled each electrode in terms of it being positive or negative. Notice the positive electrode is where the positive side of the power supply is, and the negative electrode is where the negative part of the power supply is. But also, they've also reminded us about that we can give these electrodes different names. So a positive electrode is the anode, and the negative electrode is the cathode. I think I've got it on a later slide, but we can remember which is which with the mnemonic panic. So positive anode, negative is cathode. Okay, so we're sort of getting ready now to sort of begin to think about actually answering the question, but we've just used this time to start with to just get our head around what it is we're looking for or looking at, and it's helpful for us to have just thought about the ions that are present. So if we think about what would be attracted to the negative electrode, then it's going to be the positive ions, and we have 2 positive ions. We have H plus and Ag plus. And if we think about the positive electrode, then we know that the negative ions are going to be attracted. So we've got the nitrate and the hydroxide ions being attracted to it. So then it's asking us to name the product discharged at each electrode. So when we look at the negative electrode or the cathode, that's where the positive ions are being attracted. The way that we decide which ion is being discharged or what the product is we look at which of those 2 positive ions, if those elements were in the reactivity series, which one would be the lowest in that reactivity series, which one of them is the least reactive. And so this does rely on you remembering your reactivity series. So I've written a version there. And I thinking about what could help you in trying to make it even sort of simpler. I think typically what they have in these sorts of questions is they either choose something that you can probably more readily identify as being a reactive metal, so a group 1 or group 2 metal. So we've got potassium, sodium, and magnesium there, and then the other ones, the ones that are going to be below hydrogen, because in a solution there's always going to be hydrogen, because it comes from the water. All of the metals that are below hydrogen, you can think of them as being ornamental metals, things that you could imagine being used in a decorative sense. So we've got silver, we've got hydrogen. We can see that silver is below hydrogen. Silver is also clearly a decorative metal, and so our product at the negative electrode is going to be silver. So it's the least reactive of those two elements. And then in terms of the half equation, well, the half equation is going to represent the silver ion turning into the silver atom, right? So it's going to go from being a charged ion to being an uncharged atom. And so we have to think about what has to happen for that to take place. We need to remove that positive charge, and we remove that positive charge by adding an electron. So there's our half equation for the production of silver at the negative electrode. Then we're looking at the positive electrode, the anode, and we've got a choice here. We've got nitrate and we've got hydroxide being attracted to the positive electrode. And our general rule or basic rule to decide what the product is at a positive electrode in the electrolysis of a solution is that if there's a halogen present, or it would be a halide ion, but if there is a halogen present, then that's what's going to be produced. And if there isn't a halogen present, then it's going to be oxygen. And when we look at our two negatively charged ions, neither of those is a halide ion. Neither of those feature in group 7. So our product is going to be oxygen. So if it's not a halogen, it's oxygen. So we get oxygen produced. And then the half equation for this, for the formation of this product here, this is unquestionably the hardest half equation in the course, and is quite a difficult one to deduce. So it's probably one that you're probably best remembering, given that oxygen is a possible product in lots of different solution electrolyses. So we got this. Obviously, the oxygen has got to have come from the hydroxide. Well, I say obviously, well, it is, okay. It comes from the hydroxide. And what happens is that hydroxide becomes water and oxygen, and then that is actually a mistake. So I should have 4 electrons there. So sorry about that. Let's just correct that. That's a bit of a bad one, isn't it? All right. That's very silly. So just make that correction there. So I'm sorry about that. So obviously, when we're looking at equations, one of the things to remember is that the total charge on each side must be the same. So the total charge on the left is 4 minus, because we've got 4 minus 1 charges. And so the overall charge on the right must also be 4 minus. So that is why we need 4 electrons. So now they're using the same apparatus, but this time they've got a different solution. They've got sodium chloride solution. So we're going to do the same thing. We're just going to think about which ions are present. So the sodium chloride means that we've got sodium ions and chloride ions. And then we know that because we've been made aware it's a solution, it's going to have the H plus and OH minus ions. And they tell us that hydrogen and chlorine are produced. So if I list those ions and then just cross out the H plus and the Cl minus, they're asking us to explain how another different product is formed during the solution. So they're not just asking us to say what the different product is. So we can see from these ions that there's going to be sodium hydroxide, but we have to explain it. So we have to explain how we get from here, right, from all of the ions. So it's, if we're talking about the explanation, it's from the moment, or from just before we put the electrodes in and switch on the power supply, to essentially the end when all of the products have been formed. So this is a 4-mark question. So there are two things to this. One is recognizing the fact that you're going to have sodium hydroxide, and the reason is because the hydrogen and chlorine are being produced. But just because they've told you this, you've still got to use it in your answer. It's still got to feature in your answer. So it's recognizing that, but then also thinking about, well, what is it I actually have to say to get 4 marks? And I think in a sense that's the trickiest part here. So the thing is to state the facts, to state the sort of process, to say what is happening from the very beginning to the very end. And so at the start of the electrolysis, as we've already said, we have 4 different ions. So just to state that as a fact in the beginning, because them saying hydrogen and chlorine is produced does not they haven't said that there are hydrogen ions and chloride ions. I know it sort of seems obvious, but that's an implied thing. It's not a factual statement. So you should make that statement. So you're making the statement there are these 4 different ions. And then during the electrolysis, you take the hydrogen and you take the chlorides separately. You say that during the electrolysis, the hydrogen ion is discharged at the negative electrode. So you're actually saying which electrode it is. So here they just said that hydrogen and chlorine are produced, but now you're saying, oh, apologies, actually they do point it out here. So, but you're saying that the H plus ion is discharged at the negative electrode, and the chloride ion is discharged at the positive electrode. So we've already got 3 marks. So we've got 3 marks actually without saying what the other product is. So we're saying that what we've started with, what happens during the electrolysis, and then as a result of that, at the very end of the process, we've got sodium ions and hydroxide ions left behind. So that don't think that is a difficult answer, but I think what probably would have been difficult is for you to appreciate quite what you needed to write to get these 4 marks. So the points themselves are not difficult. I'm sure you felt reasonably aware of those, but it's the fact that those were the things that you needed to write. So, you know, chemical reactions are a little bit like stories. They have a beginning and they have an end, and sometimes you'll also be able to talk about the middle, and that's what we're able to do here. So our beginning is the yellow, our end is in the grey, and our sort of the middle part of our story is in the orange and the lilac. So moving on to a different question. So here they are, we have got copper sulfate, and again, look, they've said solution. So notice that the hard questions quite often are electrolysis questions involving solutions, and so those 2 extra ions, the H plus and the OH minus ions, are something that makes these questions harder than maybe a molten electrolysis question is, because you have to remember them, and then you have to remember the rules about which ion is discharged, or what the products actually are. So what have we got? So they've used this word inert. It's not important in the sense of the question, but we may as well use it as an opportunity to explain what it means, because it does feature occasionally. So all they mean by inert is unreactive. So all they're saying here is that the electrodes aren't reacting with anything that's in the solution, and so all what's happening in the solution is to do with the actual electrolysis itself. And they ask us to draw and label the apparatus. So obviously we've just seen the previous question, which has given us a big clue, and this is only 2 marks. So you know, this is what they wanted, and I'll explain where each mark was. Now, if you put a lamp in there, and you know, often I would recommend that you do put a lamp in your diagram, which I haven't done here because it wasn't necessary, but I would generally recommend that you do. If you put the lamp in there, you're not going to get penalised, okay? So what they were looking for was a power supply, and I've got a power supply with wires attached to electrodes. That's what they wanted. And then the second mark was making it clear that the positive electrode was the anode and the negative electrode is the cathode. So that isn't immediately obvious. So I think you want to get into the habit, and I think the diagram on the previous question is actually a really useful reference point about what it was showing, and therefore maybe what you should always show is that please, you should label the electrodes in the correct way. And there is that mnemonic that I mentioned earlier, panic. So positive anode, negative is cathode. It's just a way of remembering which is which. Now this is an interesting question, and a slightly tricky one as well. So what won't necessarily be immediately obvious to you, although hopefully during the course of the GCSE it will begin to stick in your mind, is that copper sulfate has a very vibrant blue colour. So this solution that the electrolysis is taking place in would be a very vivid blue. And what it's saying here is during the electrolysis, the colour fades. So it goes from that sort of vivid blue, and it gets paler and paler and paler, and possibly goes colourless at the end. But it depends on how long you run the electrolysis for. So it's asking us why it fades. Now, this is, I guess you might not know this already, but copper ions are what are causing the blue colour. So the reason that copper sulfate is blue is because of the copper ions. And one of the things that we would have to appreciate is what the products at the negative electrodes would be. Now, copper is an ornamental metal, or can be an ornamental metal. I mean, obviously it's used for other things as well, like electrical wires and water pipes. And the reason it's used for water pipes actually is because it's unreactive. It's a very relatively unreactive metal. It doesn't react with water. So copper is going to be what's formed. So they've told us that the copper is being produced. So we know that copper is being produced at this negative electrode. So that means the copper ions are becoming copper atoms. And if the copper ions, this is the key bit, if the copper ions are causing the blue color, and then those copper ions are becoming copper atoms, then that means the concentration of copper ions is going to reduce or decrease during the reaction. So we might have lots and lots of copper ions at the start point. That's why it's quite a strong blue. And then as they're turned to copper atoms during the electrolysis, there are fewer and fewer copper ions in the solution. And as the number of copper ions decreases, therefore the concentration decreases, and so the color becomes paler and paler. And then it asks us to explain how copper is produced from copper 2 sulfate solution by electrolysis. And it really is just, again, giving a series of steps. So state the fact at the beginning that copper ions are positive. So that means they're going to be attracted to the negative electrode. When they get to the negative electrode, they're going to gain electrons, and they're going to be reduced to form copper atoms. So I think what's tricky is understanding and recognizing what the points are that you need to put to get those 4 marks, but I don't think the points themselves are tricky. So copper ions are positive, they're attracted to the negative electrode, where they gain electrons and are reduced to copper atoms. So you're really spelling everything out. You're spelling out what happens from the moment you turn the power supply on to the moment you switch it off, to the moment that the copper is produced. That's what you're describing. And you're describing them, if you're going to say they're going to go to the negative electrode, you needed to have said that they were positive in the first place. What happens when they get to the negative electrode? They gain electrons. What does that mean? It means they now form copper atoms. They've been reduced. So this isn't to do with electrolysis, but it's useful. It's good for us here, and it also explains why this whole question is considered a hard question, in that it's got a quantitative chemistry aspect to it now. So it gives us an opportunity to look at a quantitative chemistry question, and also it's one of the ones which is to do with concentration, which is also something that we sometimes find challenging. So it gives us an opportunity to recap that. So they've given us an equation. So this is, they say a displacement reaction. It's a redox reaction. They wouldn't really allow displacement in an answer from you, so it's a bit unfortunate they use it here. But anyway, so we've got copper sulfate and iron, and basically the copper will be reduced. The copper 2 plus ions will be reduced to copper, and the F ion atoms will be oxidized to become Fe2 plus ions. And it's asking us to calculate the minimum mass of iron needed to displace all the copper from 50 centimeters cubed of copper 2 sulfate solution, and then they tell us the concentration. So notice, if you look at the way they describe this, they say concentration is mass per volume. So they basically give us the equation by giving us the units. They give us the equation. Concentration is mass divided by volume, but they tell us that the volume is in decimeters cubed. Now we are given a volume in centimeters cubed, so we need to convert that to decimeters cubed. So this is an area where it's quite common to make a mistake. So you need to appreciate how to convert from decimeters cubed to centimeters cubed and vice versa. Now if we want to go from centimeters cubed to decimeters cubed, we've got to divide by 1,000. So we divide off 50 centimeters cubed by 1,000, and now we've got a volume in decimeters cubed. We are trying to work out, initially we want to work out how much copper is actually produced So we need to rearrange this equation. So now it's mass equals concentration times volume. So the fact that they've given us a volume of copper sulfate, the fact they've given us the concentration of copper sulfate, that is telling us where we should be starting. We should be starting with the copper sulfate. They've given us a volume, they've given us a concentration. So the thing that we don't know is mass. So let's rearrange it so that we can work out what the mass is. And then we put those numbers in. So there's the concentration, 80 grams per decimeter cubed. There's the volume, 0.05 decimeters cubed. So we get a mass of 4 grams. And when you have a mass of a substance, the next thing you should do, and particularly there's a big clue, the fact that they've given us relative atomic masses, if they ever give you numbers in a question, you will have to have used them. So, you know, we needed to use the 50, we needed to use the 80, and we are going to need to use these relative atomic masses. So we have the mass of the copper sulfate, we have atomic masses. So one of the things that we can do is work out the MR of copper sulfate. And from that, we can work out how many moles of copper sulfate we have. So the moles of copper sulfate is mass divided by MR. MR is the total mass of all of the atoms in the formula. So copper, sulfur, and 4 oxygens. So copper, sulfur, and 4 oxygens. So our number of moles is 4, because that was the mass that we worked out, divided by the MR, which was the total of all of the relative atomic masses of the elements in that formula. So we have this number of moles, 0.0251 moles of copper sulfate. And when we look at our reaction equation, look, I've done this ratio here. So I think it really helps to put ratios above reaction equations. And our ratio of copper sulfate to iron is 1:1. So that means if we had 1 mole of copper sulfate, we would need 1 mole of iron. If we have 0.0251 moles of copper sulfate, that means we're going to need 0.0251 moles of iron. So our ratio of copper sulfate to iron is 1:1. So that means we need 0.0251 moles of iron. And now we have moles of iron. We have the relative atomic mass of iron. So from that, we can work out the mass of iron. So mass equals moles times MR. So there with the moles we calculated, that's the relative atomic mass, because it's just iron, it's just Fe. And so we get a mass of 1.40 grams. All right, so here's a question about aluminium, because that is one of that's like the special case when it comes to molten electrolysis. So it's also often a slightly harder style question, I guess. Here they're just giving us information about the process of turning the ore, which is bauxite, into aluminium eventually. So initially we've got the ore, which is the rock, which is, makes it economic. Rock, remember, ore is a rock that's economically it's worth extracting the metal from an economic point of view. So they refine the ore into just pure bauxite, into bauxite, and then that bauxite is purified into aluminium oxide, and then the aluminium oxide undergoes electrolysis, and we get the aluminium as a product. So we actually have some quantitative chemistry to start here as well. So notice how questions in chemistry are very rarely just about one single topic. They do sort of combine stuff. So they're asking us for the calculation of bauxite that's converted into aluminium oxide. So we've got 2,500 kilograms of bauxite. We've got 1,950 kilograms of aluminium. So our percentage is going to be the 1,950 over 2,500 times 100%, which is 78%. Okay, so 78% of the bauxite is converted into aluminium oxide. Then they ask us to show by calculation that the mass of aluminium produced, so this 1,000 grams here, is less than that expected from the 1,950 kilograms of aluminium oxide that we started with. So you should state the difference in the mass of aluminium expected and the mass of aluminium produced to 3 significant figures. So what we've got to find out first of all is, well, what should we have made, right? What should we have made from this 1,950 kilograms? And one way to approach this actually is to just do percentages. So we could think about, well, what is the percentage of aluminium in aluminium oxide? So we have, for every Al2O3, that's the aluminium oxide, we have 2 Als. And so we think, well, what is that percentage as a mass? And look, again, they've given us the relative atomic masses, so we're going to have to use those. So 54, because it's 2 times 27, over 102, that is the 57 plus 3/16. So we get a percentage of 52.9%. So 52.9% of this aluminium oxide is aluminium. So if we were extracting all of the aluminium, we would be extracting a mass of 52.9% of the 1,950. So that is a mass of 1,032.35 kilograms. So we, for the difference, the mass that's not collected is the difference between what should have been and what was. And then, of course, we've got to give it to 3 significant figures. And I should have written kilograms, so apologies. So it's 32.4 kilograms that, for one reason or another, wasn't actually collected. And then this is really the main bit about electrolysis. So this is the bit where we have something that is different. It is still basically the same apparatus we have. There will be a power supply and there will be a complete circuit. It's just not shown. We've got our positive electrodes, and unusually we've got the negative electrodes sort of lining the container. And both of these are made of carbon. Both of the electrodes are made of carbon, and that's very important. So 3 marks. This is a classic question, or at least what this is asking about is a classic thing when it comes to aluminium exam questions. So why does the carbon anode, right? Why does the positive electrode, which is made of carbon, need to be continually replaced? So we have to think about what is present. What are the ions in aluminium oxide? Well, clearly there are aluminium ions and there are oxide ions. So that means oxygen is going to be produced, right? The oxide ions are going to be attracted to the positive electrode, and there they're going to be discharged and forms oxygen. So oxygen is going to be formed. But oxygen is a very reactive element, and it's going to react with the carbon. And so it's going to produce carbon dioxide. Carbon dioxide is a gas. So this carbon, or the carbon in these electrodes, is gradually going to become part of carbon dioxide, which is a gas which gets escape. So these are going to wear away. Over time, as they react with oxygen, as the carbon reacts with oxygen, these electrodes are going to wear away, and every so often they need to be replaced. So they're continually being replaced. And then here's the half equation. They've given us a half equation, and this is an unusual question, but an interesting one. They're asking us to calculate the number of moles of electrons needed to produce 1,000 kilograms of aluminium. So how many moles of electrons do we need to produce 1,000 kilograms of aluminium? The first thing to pay attention to is the fact they've given us the mass in kilograms. And whenever we look at relative atomic masses, when we're using them, when we're doing MRs or ARs, you've got to remember that we do them in grams. So chemistry is really, it's always done in grams, and yet they've given us something in kilograms. So the first thing we should do is to turn the kilograms into grams, right? Because we need to make sure the units we're working with are the same. So we work out how many moles of aluminium that is. So we know it's 1,000 grams, sorry, 100,000, it's 1,000,000 grams. We know that the relative atomic mass is 27. So moles is mass over MR or AR if it's just an element. So we get 37,037 moles. And notice again, what have I done? I've done a ratio above the equation, just really sort of spells it out for me. So it's a 1:3 ratio. So the ratio of aluminium to electrons is 1:3. So we're going to need 3 times as many electrons as aluminium. So we're going to multiply our number of moles by 3. So there we get our answer. But then finally, we just got to make sure that they've asked us to give the answer to 3 significant figures. So we give it to 3 significant figures, and there we go. So I hope that was useful. You may want to go back at the video and maybe pause at places or whatever. But if you have any queries, just let me know.